Hi, my name is Adithya, and along with my project partner Kaishavi, we'll be demonstrating machine learning and deep learning as part of our laboratory and assignment for the course EE542. Right. So for our assignment, we are supposed to apply our ML and DL algorithms on our UCI ML repository, which basically consists of the banknote authentication dataset. So the features are skewness, kurtosis, entropy, and variance, and the label is whether that particular banknote is forged or genuine. Right, that's the data set that we have in our hand, and the first task is to basically doing an exploratory data analysis. So we make scatter plots and basically color our data just to get an idea like whether how many points are genuine, how many banknotes are forged, based on our skewness, kurtosis, entropy, and variance features, and then applying machine learning and deep learning algorithms and trying to change parameters and see whether the change is significant or not. And we train our model for the first. So basically, we create a test set from our data set and a training set. So we keep the test set, that is the 0 to 200 rows, and the 0 to 200 rows for class 1 and class 0 as test set, and then we train our model with the remaining rows as part of the training data set, right? So with the whole data set, we performed our exploratory data analysis, and these are the outputs that we got. So first is skewness versus kurtosis, skewness versus entropy, versus skewness versus variance, kurtosis versus entropy. So the colors basically represent 0, 1. 0 is basically it's a genuine note, and 1 means it's forged. And then kurtosis versus variance, and entropy versus variance. So we performed all permutation of the graphs possible with our features, right? So that was the first task. So this is our Python notebook for plotting all the data. It's just a simple pandas data frame read. We read via CSV, but it's actually a text file, and we give the header names for the file. And with that, we just group by label and then plot. That's it. It's as simple as that. We're using different x and y axis because we're supposed to do with all permutations.
So machine learning on AWS SageMaker. Here I have implemented 4 machine learning algorithms to predict the banknote if it is forged or not. So the algorithms are following: linear regression, support vector machines, KNN, which means K nearest neighbors, and random forest. So training and testing accuracy along with F1 score is also calculated. For each algorithm, I have tuned hyperparameters to get maximum accuracy and analyze the change in the accuracy with respect to various parameters. So the first is linear regression. It is based on supervised learning and performs a regression task. It gives a prediction value based on independent variables. X-axis is independent variable and y-axis is dependent variable. So here we don't have any hyperparameter to set in linear regression model. So now let's see the code. So from the code, these are the libraries we need to include to perform our task. These are for SageMaker. The Boto 3 is to create S3 bucket and call the file from the S3 bucket, and this is for display, and these are for classifiers and plotting the scatter plot. So yeah, these are the configuration given on the AWS side to create the S3 bucket and import the file or download the file from the S3 bucket. So here I have created a S3 bucket, and now I'm importing the file of our data set from S3 bucket here. Let's execute the code. So here we can see that there are 4 features: variance, skewness, kurtosis, and entropy, and these are the label 0 and var for forged and genuine nodes. So Let's plot the scatter plot. Scatter plot is between two features like variance and skewness. So here we can see the scatter plot for forged and genuine banknotes, and this is between entropy and variance, entropy and skewness. Now, as the problem statement says, here we also need to differentiate part the data set into training and test. So for the test data set, we need to take 200 rows of class 0 and 200 rows of class 1. So for that, I've used the grouped by function to group the data set into two parts. One is for zero, label 0, it means for forged and genuine. So this is as it is labeled 0, it means that those are the genuine banknotes. So it is stored in a new data frame genuine, and the other one is forged. Now I'll use the ilog to take 200 first 200 rows to for the test data set from both of the groups, genuine and forged. So here we can see that. So it is, there are two groups, we can see two new data frame. Then I have taken first 200 entries for test data set and again 200 for test data set from genuine, and now I have merged those values. You can see this is the 400 rows. I have merged those values. This is our test set, and we can see this is our training set. So now I have created X train and Y train for training set, and X test and Y test for testing set. So for in X test or X train will be having the features, and the Y train and Y test will be having the label. So now we come to the linear regression model. So we have given the input as X train and Y train. To train the model, we are using fit function for that. And now it is, so we'll get the prediction, and then we'll find the accuracy using accuracy underscore score. We need to round it because here the Y prediction will give the probability. So to match with our genuine and fake notes, I have rounded to 0 or 1. So it gives this much accuracy for the training set and this much accuracy for test set. And this is the F1 score. Now we'll come to SVM. So SVM, a support vector machine algorithm, is used to find a hyperplane in an n-dimensional space where n is the number of features. Here we have 4 that distinctly classifies the data points. It finds a plane that has the maximum margin, which is the maximum distance between the data points of both classes. Maximizing the margin distance provides some reinforcement so that future data points can be classified into more confidence. So here we have 4 classes, so it will distinguish between 4 classes, and there will be 4 hyperplanes. So 3 hyperplanes distinguishing 4 classes. So data points falling on either side of the hyperplane can be taken as in the different classes. So there are total 3 parameters for which we are going to see for support vector machine. That is kernel, gamma, and C. So what is kernel parameter? It defines which kernel function we want to use to create hyperplane. So there are 4 kernels: linear, polynomial, RBF, and sigmoid. So let's go to the code and run this. So I have So let's execute with default values. Okay, so let's first execute with RBF filter. Sorry, RBF. So it is giving very good accuracy and F1 score. Let's try with sigmoid. Sigmoid. It is giving very bad accuracy respect to RBF. Then let's try linear. This is better than sigmoid, but not better than RBF. Now let's try the final one, that is poly. Yeah, the training accuracy is good, but the testing accuracy is not up to the mark as RBF. So we'll say that RBF is the best kernel for our data set. So now let's go to the gamma parameter. So it defines how far the influence of a single training example reaches. If gamma value is high, then every point has close reach. Boundary will depend on only close points to it. More weight on close points and ignoring the points which is far from the boundary that we can see in the picture. If gamma value is low, then every point has a far reach. It is exactly opposite to the above. So it gives a linear boundary. So now let's keep the value as 1, and we have seen that it is giving very good accuracy and F1 score. Now let's keep it to 0.01. It is not good as before. So as we are decreasing the value, the accuracy is decreasing. Yeah, this also goes with the sentence I said before. It is with the decreasing value of gamma, the accuracy and F1 score is decreasing, as we have seen in the description of this. So for our data set, the best value of gamma will be the 1. So let's keep it 1. Now let's go to C. What is C? So C parameter, it controls trade-off between smooth decision boundary and a classifying training points correctly. So it decides how many training points we are allowed to be misclassified and let the boundary be more linear or smoother. So for that, let's take the C is equal to 1, and as we know, it is giving us very good values of accuracy and F1 score. And then let's keep it. Let's decrease the value of C. It is the accuracy and F1 score is decreasing. So we can see that if we decrease the C, the accuracy and F1 score is decreasing very badly. So best value of C for our data set is 1. So the final parameters for our data set for SVM is kernel should be RBF, gamma should be 1, and C should be 1. So we'll get a good accuracy. We can see here it is 111. Now let's go to KNN. So K nearest neighbors, it is a simple and easy to implement supervised machine learning algorithm that can be used to solve both classification and regression problems. So it assumes that similar things are near to each other and it creates cluster of near neighbors that we can see from the picture. Now there are two parameters for at KNN. One is and neighbors and the weights. So and neighbors parameter is it's a number of neighbors means the value of K here. So default value of and neighbors is 5. So let's try it on the code here. We can see that the default we have set the default value And now let's run it. It is giving us a good accuracy and F1 score with the uniform weights. Now let's keep it 100. So when we increase the So when we increase the value of n neighbors, our accuracy and F1 score is decreasing. So if we keep 150 as n neighbors, let's see. So again, it is the accuracy and F1 score is decreasing. So we can conclude that the best value of n neighbors for our data set is 5. Now let's go to the weights parameter. So it has two values. One is uniform, one is distance. So uniform means uniform weights. All points in each neighborhood are weighted equally, whereas distance means the weight is the inverse of the distance. In this case, closer neighbors of a query point will have a greater influence than neighbors which are further away. So the default value is uniform. Now let's check that with the 5 neighbor values. The default value uniform is performing very well. If keep the distance, it is performing same. So here we can conclude we can set any value of weights for our data set because it is giving the same accuracy and F1 score. Now let's come to the random forest. So random forest classifier creates a set of decision trees from randomly selected subset of training set. It then aggregates the votes from different decision trees to decide the final class of the test object. And the advantage of random forest is that it won't overfit the model and handle large amount of the data set with higher dimensionality. Here we can see in the model that there are three trees and three classes, and now they are calculating the votes and deciding the final class. So there are also two parameters for random forest. One is an estimator parameter. This is the number of trees you want to build before taking the maximum voting or averages of predictions. The higher number of trees give you better performance but makes your code slower. So we should choose as high value as your processor can handle, because this makes your predictions stronger and more stable. So the default value is 100. Let's try with the default value. So the default value of it is giving a quite good accuracy and F1 score. Now let's take estimator as 10. So what happens when we decrease the value of an estimator? When we decrease the tree, it reduces the accuracy as we have seen before. Now let's keep it 200. So it is giving almost the same accuracy as 100. So it is now saturated that after 100 it doesn't matter that how much we keep the value of estimators or trees. So we'll keep that the best value of an estimators for our dataset is 100. Now what is max step parameter? Maximum number of levels in each decision tree. Default value is none, which means nodes are expanded until all lives are pure or until all lives contain less than minimum number of samples required to split an internal node. So let's take the default value as the default value is none that we have seen. Now let's keep it 100 and estimators and depth is 5. Okay, we can see that the accuracy is good enough. Now let's keep the accuracy decreased, and if we take it as 10, we are getting the max accuracy and F1 score till now. So we can conclude that the best value of max depth for our dataset is 10. So here we have executed 4 algorithms for uh, banknote authentication dataset. So from the results of accuracy and F1 score of 4 algorithms, we can observe that SVM and KNN gives best performance. So now to decide the best algorithm for our dataset, we measured the time taken to train the model. So let's get back to the code. Here we have used time function to observe the time taken to train the model. So we can see that it is taking 0.069 seconds, and the KNN model is taking 0.0075, which is much lesser than SVM. So we have decided to move on with the KNN algorithm because it is taking lesser time and giving best accuracy and F1 score. So this way we have completed machine learning in our lab 10. Now we will go to deep learning.
So let's now go over to the deep learning algorithm that I used. So first things first, we import whatever is necessary, right? And then we read a data frame using pandas, and then we create a separate test data set and a data set. So the data is actually the training data set, and the test is actually the, as it suggests, it's a test data set, right? So you can see this is the first 10. So data.heads gives us the first 10 value, first 10 rows, and same for test, right? So from that, from our data, that is the training data, we get our y train. Y train is nothing but the label column, and we get the x train, right? We convert that to numpy just for compatibility purposes, and then we normalize our x train and x test and y train and y test, right? And then this is our core of the program. So we are using neural networking, right? So we flatten it. So this becomes our first hidden layer, this becomes our second hidden layer, and this is our output layer. So you can see that I'm using 128 units. So that this signifies how many nodes that I have in my hidden layer 1 and hidden layer 2. And you can see that output layer is only 2 because at the end the labels are either 0 or 1. That's why you're using 2. And it's always recommended to use softmax so that we get a probability distribution, right? So you can see that I'm using a scaled exponential linear function activation function because I was observing that with this I was getting the maximum accuracy, right? So this is the syntax for compiling the model. We're using an atom optimizer, and then we fit our model with our x train and y train. So epochs signifies how many times it will repeat, basically how many times it will repeat the whole training the model. So I've done it 3 times, so you can see that our accuracy keeps improving for all the 3 times, right? So with that, we first calculate the training accuracy. So we have training loss this much and training accuracy as this much, right? And then we evaluate with our test data, slightly less but more or less the same, right? And then we then predict our F1 score for our test data. So it also comes out to be this, right? So let's try varying our epoch. So let's start with 1. Let's see how that's gonna turn out. I'm gonna restart and run all. Yeah, so you can see that the accuracy dropped because there's only one cycle of training, right? So the more number of cycles, the better your training is. That's the gist, right? So if I do five, let's do five. You can see a significant improvement there. Yeah, you can see that after every cycle, the accuracy is improving and improving, and you can see it's always 0.99, 0.99, 0.99, which is almost too perfect, right? So the caveat is that it's unnecessary, basically unnecessary complexity. I mean, it's just goes around and around, right? So it's I for my it's just my preference that I should keep three, and even with three epochs, it's giving us a decent number. That is 0.98, 0.99, which is decent enough for me, right? So let's keep now epochs constant. Let's try to vary our number of hidden layers. So yeah, let's just first let's start with just one hidden layer. So if it's just one hidden layer, it doesn't basically qualify as a deep neural network. It's just a neural network, simple neural network, because it just has one uh, hidden layer. So you can see a drop in the accuracy. Yeah, so it's 0.95. So why are we getting pretty accurate? Because the data set is too small. It's just 1,000 instances. So that's why it's easier to train 1,000 instances. It's not that much, right? So let's uncomment this. So now we have two, right? Let's just restart and run all cells. Yeah. So you can see that the accuracy improved. Even the F1 score improved, right? Let's try adding one more hidden layer. Let's see how that's going to turn out. So I have three hidden layers and one output layer and one input layer, right? Seems kind of redundant because it's only 1,000 data sets. It's not really necessary, but you can see that we are getting near perfect accuracy, right? So that's nice, but it's not really, it's like overkill, right? So it's not really needed. So we've done that. So let's now try to tinker around the activation function. So let's first start with the rectifier linear function. Yeah, you can see that it's 0.98, less than what scaled exponential linear was giving us, right? So that was ReLU. We already seen CeLU, and let's try to. I'm just thinking of different activation functions that we can use. Yeah, let's use soft sign. Let's use soft sign. Yeah, more or less the same, but still not as good as what CeLU was getting. So let's stick with CeLU. Right. So these are the parameters that you could alter and change based on what you want and how you want it, at the expense of anything if there is any constraint, right? So we're back to CeLU, and you can see that CeLU is slightly better, right? It all comes down to preference, and it's like a hidden trial thing. And yeah, you could always alter this to something better. Like, let's try one more function. Hmm, let's try soft plus. Yeah, let's see. Yeah, well, you can see that soft plus is definitely not as good as the rest of the activation functions, right? You can see it's a huge drop in terms of the accuracy. And so let's stick with what we were getting a good values with. So these are the way that you can tune your hyperparameters, like activation functions, the number of neurons in your hidden layer, and the number of hidden layers as such. So now you can see that Selu is giving us near perfect scores, right? So you can get an idea like what to use and how to use. And yeah, this concludes the deep learning section.